last talk of the program. We made it. Isn't this great? Ilya Grigorik is one of our lifer speakers. He's spoken at every Gogoruko, and that's just because he's an awesome speaker and he always has something interesting to talk about. Ilya was the founder and CTO of PostRank. And which I can be forgiven maybe for getting wrong because his company was acquired and he now works for Google. So he's recently moved to the Bay Area, so we're really glad to have him here and part of the community. So big welcome for Ilya. Thank you very much.
All right, so we're coming to the end of the conference, and I'm sure you guys have crammed a lot of interesting things into your head. But let's take the next 30 minutes to actually walk over some of the things that I think are very important and we tend to overlook as engineers in building web services, high-performance web services. And I put Ruby in brackets in there for a reason because I think I will talk about a specific pattern or something that we came across while we were building this framework called Goliath, which, interestingly enough, following on Yehuda's presentation, it started as an application. It's not something that just came out, finished right off the first go. In fact, it took us 3 years and a number of rewrites, but we arrived at this thing. We open sourced it at the beginning of the year, and I think we learned a lot in the process. So this is an experience I want to share with you. And right up front, we talked about Speedy, we talked about fibers. I'm going to disappoint you. I'm not going to try and sell you on fibers or EventMachine or anything like that. I think these are tools to achieve a task. And actually I agree with everything that's been said. So, first, a little bit of a quiz. We just learned about Speedy, but I'm not even convinced that we know HTTP well enough. This is coming from my own experience. I thought I understood HTTP. Then I went out and tried to write an HTTP client, and then we wrote Goliath, and I just realized that there's a lot of edge cases that we're not aware of. So here's an example. We're using an HTTP client, and we're going to request, we're going to open a connection to the main server, to gogoruko.com. Then we're going to make 2 GET requests. One is for speakers, and one is for schedule. And I'm using something special here. I'm actually setting on the first request, I'm setting an explicit keep alive. So this is an asynchronous library. Here's the question. How long do you think this will actually take? So we know that the first request takes 250 milliseconds, and the second request takes 300 milliseconds. I'll let you guys think about it for 1 second. All right, put up your hand for A. Nobody, all right. B. Okay, C. So I think we're split, so 50-50. The answer is you're all superstars. Everybody gets a star. Because the reality is it's actually all of the above, even A. And to evaluate that, there's some truthiness to each one of these answers. And the question is, why? All right, this is absolutely ridiculous. So, in light of the Speedy talk, I was actually thinking, maybe we should rename this talk to Speedy, come on, right? It's like we can't even get HTTP right in the first place. So, let's take a step back and actually take a look under the hood as to what's actually happening on our HTTP stack when we do this. So, we tend to overlook this. There's this whole TCP handshake. We tend to think about HTTP and the actual headers and the responses that flood back and forth, but the actual handshake is actually very expensive. So, we have a ping pong or a SYN, an ACK, and a SYN-ACK, right? So let's say we throw away the last one, the SYN-ACK, because we're aggressive. There's still the double round trip time. So in most cases, when you're sitting at home and you're making a request, you're going to take 20, 30, 50, sometimes more milliseconds just to make that first request to the server. But the server also has to reply back to you, right? So you already doubled that time. So if we say that the initial connection takes 20 milliseconds, just to establish that TCP tunnel, it'll take us 40 milliseconds. And that's if we're optimistic. This is why, incidentally, why CDNs and companies like Google, Yahoo, and everybody else spends a ton of money to put servers near you, right? They want to terminate your connection as quickly as possible. Now, that may not be something that we tend to think about on a day-to-day basis when we're developing the next app kind of thing, but it is something important to think about. So what goes in, so let's say we have this TCP connection now. So what goes in from there? We got the handshake done. Now we have the request coming in, so it's the headers and the body. So that also takes 20 milliseconds, right? Once we establish the TCP connection, we need to actually send the headers. So that takes some time. Then there's the 40 millisecond or whatever amount of time that it takes to actually process the request. So here I'm arbitrarily pinning that at 40 milliseconds, which in itself is pretty fast. So you do the math and you figure out that if it took me 40 milliseconds to process the request, then more than 60% of the time was actually spent just waiting on the network, right? Which is one of the messages that Chris tried to convey, which is HTTP is slow, it's got huge overhead, we spend most of the time waiting on the network. Well, I don't think that's a function of HTTP. Now, don't get me wrong, I love Speedy. I think it's actually a very cool project and it's actually going to get wider adoption in the long run. But this is the state of affairs as of 1996. This is HTTP 1.0. Now, one thing that I've learned through doing all this work is as developers, we tend to focus on benchmarking processing time. So let me go back. It's that little piece in between. It's the 40 milliseconds, right? We write our new web service. We run our benchmarks against it, Apache Bench, Siege, whatever you use, or some load testing framework. And we optimize that little bit. And then we forget completely about everything that's around it. How long does it take for a user to connect to me? How long does it take for me to route the request between my first proxy to my actual server? And is there a queue of people waiting in there? I find that this is actually often a big gotcha that a lot of developers forget about. You optimize your one service, so you say, well, most of my requests take 10 milliseconds, but then they forget the fact that their load balancer is queuing up 100 people, right? Because they have high throughput, but they're only allowing 10 requests through. So the actual request takes a lot longer. So this is a bit more of a public service announcement. Think of the full round-trip time for your user. So we talked about HTTP 1.0. Who knows the big differences or can explain the differences between HTTP 1.1 and HTTP 1.0? It's actually just a few extensions. And the most important ones are keep alive and pipelining. So the important difference is, in 1.0, you would always terminate the connection. That was in the spec. You would close the connection after each request. So for each new resource that you would fetch, you would literally need a new tube to get your resources. Right? In 1.1, we came to our senses and said, well, that's kind of crazy. This is expensive. Let's introduce this new concept called keep alive. That means we can reuse open connections, so we don't have to do the TCP handshake. We can't do multiplexing, as in we can't send multiple data streams at the same time, because the HTTP protocol was not designed for that. You send a request and you wait until you get a response. And even more so, in 1.1, we will default to on. So if previously it was always to close the connection, then from now on, we will always, by default, keep the connection open. So that's nice. The second extension was called pipelining. And what pipelining allowed you to do was to send multiple requests at the same time. And basically, you had this contractual term which would say, well, you can send 2 requests at the same time, but they would arrive serially. Right? And this is important. If the first request takes 10 seconds, and the second request takes 5 milliseconds, you'll still have to wait for the first one to render before we can serve the second one. And this is what Speedy is trying to solve, right? Speedy says, you don't have to wait 10 seconds. We can send you the response to the second request in parallel. So, looking at the same data flow for keep alive, let's say we had 2 requests. right? So what happens? We have the 40 millisecond setup time, which is the same as we saw before. We need to send the actual request, process it, send the response back, and then we do the same thing for the second request. So at the end of the day, we've eliminated 40 milliseconds of the initial startup cost, which is creating that connection, which is kind of nice, but it's a small win over the previous design. There's one gotcha though. So the spec says that keep alive will be defaulted to on. In reality, while we can talk about optimizing the servers, enabling speedy and all of this kind of stuff, we as developers don't even take advantage of HTTP 1.1. And most of us are not even aware that we're doing this or not doing it. As an example, if you look at, and I'm not picking on NetHTTP, this is actually true of most libraries. If you look in the guts of NetHTTP, it sets this one little header for you by default, which is connection closed. And what this tells the server to do is to close the connection after you make the request. You're basically giving it a hint that says, close the connection afterwards. Don't keep the connection open. And I was building EMHTTP. I thought, hey, it'd be kind of nice if I defaulted to the same pattern because I was basically looking at NetHTTP and I said, okay, I'm going to close the connection after each request. At some point, I reread the spec and I said, you know what, I'm going to do the right thing. I'm going to not send this header and make the connection stay open. I put that out. It wasn't even released as a point release. People were basically pulling it from master. And in the span of a week, I got a whole bunch of mail and issues saying, like, your stuff is broken. I have hanging connections. I can't do anything. And I replied to all of those questions, and in the process, very quickly learned that I'm not going to win this war. Basically, the expectation that people had was you make a request, you get a response back, the connection is closed. Or at least that's how we tend to model this in our head. And I think some of this confusion lies in the fact that HTTP is supposed to be stateless. It's like stateless doesn't mean that you have to close the connection every time, right? But this is the status quo. So the good news is there are workarounds and there are improvements. So for example, NetHTTP persistent actually allows you to keep the connection open and re-request or reuse the same TCP connection to fetch requests. So if you wanted to, your browsers do this, but I find that most developers or most of our libraries don't do this because it actually requires that we think harder about how we design and how to reuse these connections. So pipelining. Pipelining is actually much more interesting. So if previously we had to wait for the first response to get back, then now we have the setup, we can dispatch both of the requests at the same time, and there's a little bit of delta in there for we are sending two requests, but basically let's assume it's 20 milliseconds. We can process them both at the same time. Let's assume that we're re-requesting the same object and it takes the same amount of time for each. Get it back. That's a 50% improvement on the previous state of affairs, which is really nice. And this is in the spec. This is allowed by the spec. So, once again, let's do a quiz. We have connection setup, which takes 50 milliseconds. The first request takes 300 milliseconds. The second request takes 250 milliseconds. Show of hands for A. B? A few hands for B. C? Okay. D? A few hands. So the answer is C. Why? Well, because we have the connection set up, so that's just a flat rate, flat tax that we have to pay for setting up the connection. That's 50 milliseconds. Then we have the first request, which is 300 milliseconds. And the second request comes in parallel, so it will actually complete before the first one is done. But it will have to wait until the first one is actually serviced back over the pipe. But there's one gotcha. So keep alive, for the most part, works. This doesn't. It is, for all intents and purposes, it is broken and disabled. So no browser, so I shouldn't say no browser. The only browser that supports pipelining by default is Opera. And even for that, it basically has a bunch of heuristics on the side when it connects to the server. It actually sometimes opens a parallel connection and says, like, let me sniff if you support pipelining. And if you do, and if you jump through all these hoops, then I will actually pipeline requests to you. And the reason for this is basically broken web servers. It's been broken for a very long time. Proxies don't play well. And on the wider web, we don't use pipelining. Now, that doesn't mean it's not useful, as we will see in a few minutes. But just so you guys know, it's not something that's actually being used. And there's an interesting proposal that Mark Nottingham and a few others are putting together for a list of suggestions for, we can't fix it, but maybe we can add some extensions that will make it work a little bit better. I'm somewhat pessimistic that this will actually go through or that we will see actual adoption. I think what's more likely to happen is that we'll just skip this entire generation and move to something like Speedy in the long run. So, with that in mind, we can come back to this. So why are all of these have a truthiness to it? For 250 milliseconds, well, it turns out that a lot of the proxy servers on the wider web actually don't pay attention to any of the headers that you send them, right? So you can ask for multiple requests, but the moment it gets the first response, it's like, oh yeah, I'm done, thanks. Right? So it'll actually close the connection to the second request. So you'll only see back your first response. So that kind of sucks. For B, we have a couple of cases to worry about. So the good case is both keep alive and pipelining works. That's what we want. The bad case is keep alive works, but mostly you get garbage. And the reason this happens is most servers, or many servers, do the wrong thing. They get the request, they service the second request, they're like, oh yeah, I'm done. Let me just send you data. And then the second request, some milliseconds later, gets finished, and it's like, oh yeah, let me send you data. And then you get two streams colliding in one, and you get garbage data out. It's beautiful when you see it. The problem is you can't predict as to what you're actually going to get. It's actually kind of fun trying to do this on like well-known web services and see what comes back. And the last one is just, it's bizarre, and I've seen this. I'm not even sure what the web server is doing, because we're asking it to do pipelining and keep alive, and sometimes you actually get them just in serial order. Sometimes it's completely bizarre. So that's the state of affairs for HTTP. But HTTP, and because of this, I think HTTP gets a bad rep, right? That's why we need a different RPC protocol in your backend and all the rest. Well, truth be told, HTTP can be a high-performance transport, and Goliath, which is the framework that we built, is actually our attempt at making this work. We didn't intentionally set out to do this, but in the process of learning about HTTP, we arrived at this solution. So, very quickly, Goliath started at, as Josh mentioned, at PostRank, which is now Google. We were doing a lot of social analytics. We did have a Rails front end, but most of our traffic was actually done via our APIs for partners and everybody else. And these were all HTTP APIs. In fact, our own services were consuming HTTP APIs. So Goliath, as we know it, is kind of the third big rewrite. It was open sourced in 2011. Very, very quickly, most of our stuff was abstracted behind HTTP APIs. In fact, most of our Rails code talked to HTTP APIs directly, so we didn't even use active record all that much. And we got a lot of, it's a trade-off. This is an instance of a design trade-offs. You can make different choices in your own implementation, but we found that this worked really well for us. one interesting observation that we made was, we did this infographic at the end of last year, somewhere back in December, and we looked at our actual API traffic, and we realized that, let's say we had 330 external requests a second coming in, we had about 500 internal requests. So what that means is we had a big fan out. So our services would call on other services, which would call on other services, and then gather the responses back. And all of this was coordinated via HTTP. We explicitly decided not to go down the route of using some other serialization or RPC protocol. So HTTP and JSON. So here are some of the design choices, or some of the things that we try to address with Goliath. Multiple requests within the same VM to lower the operations cost. So we couldn't, or we felt like we couldn't justify spinning up, many passenger processes or anything of that kind. We wanted full HTTP 1.1 support, and it turns out once you do the full survey of all of the Ruby web services, none of them actually supported all of the edge cases that we just went through. And there's not that many, but none of them actually work with everything we needed. And then the last one is kind of interesting, Ruby polyglot. So we had many instances where we would have a really nice JRuby or Java library, I should say, and we just wanted to wrap that into a web service, right? Because we coordinated everything through web services. And we wanted to reuse the same API. We wanted to reuse the same stack. And this is a problem that we run into quite often, where we'd have beautiful Ruby-powered API, and then we had this kind of a kludge Java API running side by side. So our goal with Goliath was to make it work in both paradigms. This is kind of a high-level view of what's going on. So there's the network. We are using EventMachine. We are using a streaming HTTP parser. We'll talk about that in a second. And the important distinction there is the actual HTTP parser is effectively the same parser that is being used by node.js. There's a Ruby wrapper for it, and there's a Java variant implementation of it as well. So you can actually use Goliath on JRuby and all the rest. And it does support HTTP 1.1. We have middleware, routing, all the things you would expect, and yes, even fibers. Some numbers, some interesting numbers. The full request response time through the stack, walking up and down, takes about 0.3 of a millisecond. So that gives you a rough number for what's the performance like of the stack. So, very, very simple. So we're going to walk through a couple of quick examples of using Goliath, and then I think we'll have a quick demo. So this should be self-explanatory. I'm not sure what I need to explain here. It is a rack-like API, but we are not a rack service, if you will. So Goliath, as I described it, is a web service or a web server, most and foremost. And then you can build it up from there. So Goliath is not meant to be a replacement for Rails, Sinatra, or anything of that kind. I think the best place where it fits is when you have a specific and narrow problem of I need a high performance or a high throughput web service, and I'm willing to sacrifice some of the nice things of ORMs or some of these things. You can use your ORM here, but I wouldn't recommend it because I think then you're choosing inconsistent trade-offs. So we provide a rack-like API, but it's not truly rack compatible. So you need to have special async rack middleware to make it all really work. But it's a single file. You run it. You set it into production mode. Here's where some of the peculiar things that or design decisions that we made. So we are not a rack. We provide a rack interface, but there's no rackup file because you can't run this code on any other rack-compatible server, so we don't need a rackup file. So instead of putting your use middleware statements into a rackup file, we put them directly into these classes. And one of the reasons we decided to do this also was, remember the architectural diagram that I showed at the very beginning where we had very narrow services sitting in front of specific databases? in practice, we found that we wanted to separate. We didn't want to have a big router with one monolithic app serving all the different requests. Instead, we would have small services that would serve a specific purpose, which would allow us to keep that code stable. It's tested well, and we didn't have to. It was very low churn. So single purpose, but high throughput. And because this is meant to be a web service, we provide simple built-in things like verify that you're not making a delete request when we only support get requests, or verify that you provided this parameter. So these are very simple built-in middlewares. And actually, one thing I'll call out explicitly, it is a fairly bare metal API. So you can build it up as much as you want, but it gives you nothing. It assumes nothing at the beginning. So even stuff like parameter parsing, where we're calling params echo, is not enabled by default. If you want that, you can enable it, but you have to be explicit about it. So here's a very quick example of routing. This is actually something that was added after we open sourced the project. So we didn't actually use this internally, but I think a lot of people have found this useful. So this was an open source contribution where somebody added the HTTP router into Goliath. So pretty simple stuff, should not be anything new. So we can get requests, not found routes, so on and so forth. Here's where stuff starts to get a little bit more interesting. So this is something that was not possible on any other Ruby web service. We wanted to have a completely asynchronous processing, request processing stack, where as the request is coming in, let's say when you just sent the headers, we wanted to emit an event saying, hey, I just parsed the headers. Why would you want this? Well, let's say you're accepting a 10 megabyte file upload, right? And your headers carry your authentication information. You don't have to wait for the full 10 megabytes to arrive to validate those headers, right? You could look at those headers and say, hey, your signature's wrong, close the connection. Or what if you want to take that upload and stream it into S3, such that you don't even have to store it in memory, right? You can just take the incoming connection, pipe it to an outgoing connection to S3, and just buffer that data directly into some backend service. So this gets more and more useful as the file sizes increase, for example. So this API allows you to inspect all of that data. And then, for example, the onBody handler would get called every time a new chunk of data arrives. And then the response method would get called at the very end. Likewise, you can do streaming response, or return a streaming response. So here's a little helper. It says, hey, I'm going to send back, instead of sending you a full response, I'm actually going to send you a streaming response. So send back a 202 response code, set this header. So what this will actually do is spit out the HTTP header back into the connection, but it won't close the connection. At that point, you just have this thing hanging, and you can do anything you want with it. Here's it's a silly example, but it's an example. We're setting 2 EventMachine timers. The first timer will fire every second. It'll just print hello directly into the stream. And after 10 seconds, we'll set up another timer which will fire and cancel the first one. So it'll print hello 10 times, cancel the timer, send a goodbye, and then close the connection. So pretty simple stuff. But this is how you would implement something like the Twitter streaming API, right? You could connect this to some backend system that is emitting events, and you can just stream this directly back to the client. We support WebSockets. So Goliath in itself is a pretty low-level framework on top of HTTP handling, right? So we can substitute and we can build in WebSockets on top. So this works just as you would expect. As you can see, it's a very similar API to what we just looked. And it wouldn't be too hard to add speedy, right? So we have all the right tools. We're missing the NPN handling in EventMachine, basically, to actually push it in. So that could be interesting. And yes, there's even fibers. right? So speaking of fibers. So everything I've described so far has nothing to do with fibers. But here's an interesting design decision that we made with Goliath. We do actually wrap each incoming request within a Ruby fiber, which means that Goliath requires Ruby 1.9. So why would you want this? So here's an example. We give you a choice. You can do both. You can do completely async, or you can use fibers. Here's a variant of some code written with callbacks. So you have your one frame, no stacks, no nothing, right? This is very similar to what you would write if you're writing node.js. And you can do this in Goliath. Here's another variant that you can do in Goliath. Let me just flip back and forth. You can choose which one you want to use. So what happens is we patch the asynchronous clients and we make it feel like it's synchronous. So if you want to use this, you can. And that allows you to write code that doesn't rely on callbacks. So instead of making a connection and then explicitly setting a callback and a nurback, we actually say, you know what, we'll just pause until that request is done. So we are building a scheduler into Goliath, as you would have alluded to. And then we return that object once that is done, and you can do whatever you want with it. Right? So at least in practice, this is the default mode that we use at PostRank. We find that it works really well, and it leads to easier to maintain code, at least in our own experience. How does this all work? There's a library called EventMachine, which you can look at on GitHub. It's basically a set of patches and extensions that provide some primitives for making this stuff easy, the async workflow easier to work with. So as a very simple example, we have this multi-interface which takes, it allows you to pass in multiple requests which will be executed asynchronously, and then you call perform and you wait